Okay, gentlemen, let's take a look at implicit differentiation. You want to make sure you can handle a problem like this. There's going to be at least one or two on the final. It's a dead giveaway when you need to use implicit differentiation because you'll see that it's the relationships are jumbles of x's and y's. You won't see an expression like y equals x squared minus 3. X's and y's are all jumbled together. So what I want to do is go through and take the derivative of each term with respect to x. And so what we're going to do is focus on this first expression here, the xy squared. And we're going to see this as a product, so I might even go in there and put a little dot in there to kind of remind us that that's a product. And of course, we've got the product rule. It says if you've got a product of two functions, the derivative is derivative of the first times the second plus the first times the derivative of the second. So in this particular case, we'll think of like x will be sort of playing the role of f, and y squared will be playing the role of g. So we can motor through there, and we'll say, all right, let's get the derivative of x, which of course is 1, and then we multiply that by g, which would just be y squared. Then we can come back and say, okay, now we need the original f function, which is just x, plus the derivative of y squared. And this is the clutch thing, because the derivative of y squared with respect to x is going to involve the chain rule. So I'm going to bring the 2 down in front, drop the power to a 1, and then take the derivative of what's inside, the derivative of what's inside being a y, and we'll show that derivative of y as dy dx. So we're going to get 2y to the first times dy dx. And so now we've achieved the derivative of this first term, xy squared. So now we just need to do the same thing with this next term, x squared y. So again, I'll define x squared sort of as my f and y as my g. So we need to use the product rule on that. So it's going to be the derivative of x squared, which is just 2x. And then that gets multiplied by g, which is y. Then we're going to go and take the derivative, f, original function, x squared, and then the derivative of y. And the derivative of y, again, is just dy dx. And then, of course, when we get over to the other side of the equal sign, we have the derivative of 2, which is 0. The key at this point is everything that has a dy dx will stay on one side. If it doesn't have a dy dx, it goes to the other side of the equal sign. So this guy and this guy have to go over to the right side of the equal sign. So they're going to show up there as negative. So we'll get negative y squared and a minus 2xy. Meanwhile, the terms on this side, this one and this one that have the dy dx in it, I guess I could write this first one as 2xy dy dx, and the second one is just x squared dy dx. And of course, you might remember the reason we do this is because these two guys necessarily have a common factor of dy dx, so we can factor that out. And you're left behind with 2xy plus x squared. That's, of course, equal to what's on the right side. And now the last step is just to divide this off from both sides. So you're going to get dy dx is equal to the opposite of y squared minus 2xy all over 2xy plus x squared. And that would be our dy dx. Not terribly difficult, but you just got to remember that you're always going to have to take the derivative of what's inside. So before we move on, I'm just going to maybe do another example that may be a little bit more basic, because another application of these is going to find the second derivative. So I'm going to take a new, more simple implicit relationship, x squared plus y squared, let's say, equals 16. You should know that that's the equation of a circle with a radius of 4. So if we can come through and look for dy dx on this one, we're going to take the derivative of x squared, which is just 2x. And then we take the derivative of y squared, which is 2y, but because y is a function of x, we come back and take the derivative of what's inside, which is dy dx. The derivative of 16 is 0, and now it's just a matter of getting dy dx by itself. So we will subtract 2x from both sides, and we get 2y dy dx equals negative 2x. And now we can just divide both sides by 2y. And the result is dy dx is the opposite of x over y, because of course these 2's are going to cancel out. So that's a pretty straightforward example. Now, if you're asked for the second derivative, and again, the notation on that would be this, that means we're looking for the second derivative of y with respect to x, which really just means we want the derivative of this. So the derivative of dy dx is the second derivative of y with respect to x. And now we're going to have to employ the chain rule over here. The chain rule. Well, yes, chain rule, but really the quotient rule, because we've got a quotient. So we are going to follow the quotient rule, and we're going to say low, which is the y function, times the derivative of the high function, which will be -1, minus the high function, negative x, or the opposite of x, times the derivative of the low function, which is dy dx, all over the denominator squared, which is just going to be y squared. Let's clean up our negative signs, and we're going to have the opposite of y plus x, and this is the key thing. The opposite of y comes from this. The plus x comes from subtracting the opposite of x. But now we've got this dy dx term, and we can't leave dy dx in the answer. So what we're going to do is use our solution from the first part, and this dy dx right here is going to go in for that. So this x down here is going to get multiplied by the opposite of x over y. So I'll keep that in red just so we can keep our eye on it. The opposite of x over y, and of course this whole thing is over y squared. And that's our answer, except it's not really simplified because we've got a complex fraction. We've got a fraction within a fraction. I think I taught you earlier in the year that the best way to clean these guys up is to multiply through by the LCD of all the denominators involved. And of course, all the denominators involved is just this y that's right here. So if we multiply this thing by y over y, distribute this y over to here, you're going to get the opposite of y squared. When we distribute the y here, it's going to cancel with this y in the denom, and you're just going to be left with negative x squared. All over, y gets pushed in there, and we get y cubed. So there's an answer, but since the numerator has two negative signs, you might see it factored out something like that. And there you go. There's a good example of implicit differentiation with a somewhat more complicated example, then a simpler one, but with that one going to find the second derivative. That's all you need to know for implicit.